Hello, and welcome to the first of three 45-minute videos explaining the science behind one of the three FRQs in this packet. I believe they are all 2015. Oh no, never mind. One of them is 2015 and two of them are 2019 FRQs. Alright, in this video, I will be explaining the first FRQ, the physics behind the first FRQ, and then how you go about applying those physics into the first FRQ. I will start by just reading the first FRQ, the problems, what it's asking, and then I will go into the science behind it and how you can apply it in order to solve the desired problems. So the first problem in this FRQ states that there are two identical spheres released from a device at a certain height at the same time. The first sphere has no initial velocity, and the second sphere is given a horizontal velocity of an unknown magnitude just called VO. It travels a horizontal distance d before falling on the ground, versus the first one that just falls straight down. The spheres reach the ground at the same time, even though b covers more distance before landing, and we consider the air resistance to be negligible. So the first question is to draw a free body diagram for both forces. I will not show you the answer yet. The second question is to graph the horizontal velocity components of each sphere as it falls and as time progresses. And the third question is to explain in a clear paragraph why they both hit the ground at the same time despite traveling a different distance. So let me start with the physics behind it. The first and most important, most crucial thing you need to know in order to solve this is you need to know how to break down vectors into their x and y components. You will then also need to learn about forces, about gravity, and about breaking up equations into their x and y components. And then you'll need to learn about free body diagrams, and I will explain all of those. I will start by teaching how to break down vectors into their x and y components. This is crucial for this problem as there are two dimensions involved. It is not a one-dimensional kinematic equation, which means you have to consider both dimensions, and how to go about doing that is by breaking down things that are in both dimensions, such as a vector that is not completely horizontal or completely vertical, and learning how to break that down into both of them and then apply that new variable or that new value for both of them into a kinematic equation. First things first, when going about breaking up a vector, you need to designate your reference points. You need to designate what is your x direction and what is your y direction. This may seem obvious, but this direction doesn't always have to be x and this direction doesn't always have to be y. You can change the orientation based on what makes the problem convenient. In this problem, just completely horizontal is simpler to leave as x, and completely vertical is simpler to leave as y. So make sure in the very start of your problem you have something that looks like this. This also tells us in what directions we want to break up our vector, as we want to break it up into the components that are parallel to the reference axes. Okay, so say you have any velocity or anything you could break down. You could be breaking down direction, you could be breaking down acceleration, you could be breaking down initial velocity or final velocity, but it's all the same. There's all the same process for having to solve it. They all have the same process. So say you have a random vector that's clearly going in multiple dimensions, both dimensions. You can start by drawing the horizontal and drawing the vertical to that vector, and you'll know that you'll want to break down the vector into lines that follow that horizontal and that vertical. So first thing you'll want to do is observe the angle that it makes with the horizontal, as that is very important for calculating the value of the horizontal and vertical vectors. Say the vector has an unknown value. I'm going to give it VO, as that is the same that we are using in this equation, or as in this FRQ. So this has the value VO, and the angle is theta. Let me get that so you can see it. Yeah, that's VO, and that's theta. Okay, so the first thing you want to do is you can find the values of the components you break it into using trigonometry. So first things first, you can break it down into two vectors because adding vectors just is equal to overlapping the first two, and wherever they go is the same as the final one. So say you have a vector like this. It doesn't matter how you break it down into multiple vectors as long as the final endpoint is that. So you could break it down into like 15 different vectors, each that add on to each other, as long as the tail end of the first one, of the end one, links up to the first end of the first one, and it links up to the matching point you want to do. So you can add these vertical lines here. Look, I just do like 15 different vectors that all add up to that original vector, because as you can see, this one vector that I highlighted goes straight from there to there, and you can have a vector going down and then around and then around. As long as it gets back to the same point, you can add those vectors, and the addition of all those vectors will be equal to the original vector. So this means, for our simplicity, we're going to break down the vector into its horizontal and vertical components. As you can see, you can do it sort of like a right triangle. Say you have a desired vector here. You can break one horizontal, and then meeting that end, you'll break another vector completely vertical. And it should reach up and touch the original vector, and therefore be equal to it. As you can see right here, that's not a very good drawing. Let me get one better. Now you may say, well, how do you go about finding the values of these new vectors? Well, assuming this one is VO, as we already stated, we can find it using trig, assuming the theta is known, or you can just call it the variable theta. As you can see, the variable that's horizontal is the adjacent side to the angle, and the variable that's opposite to it is the opposite side to the angle. And as you can see, the VO, the vector we are trying to break down, is the hypotenuse. This makes it very simple when trying to solve trig. I have labeled up here, it'll go in the screen, there's VO, there's the theta, there's the adjacent side, and there is the opposite side. Okay, so now using trig, we can break down this VO into this horizontal component into VO cosine theta, because that's all it really is, as we know from trig and as we know from the unit circle. And we can break this bottom one into VO sine theta, this vertical one. So I should have them labeled right here. You have VO, VO sine theta, and VO cosine theta. As you know from the unit circle, assuming that a line has the radius 1 on the unit circle, the horizontal component of it will be the cosine, and the vertical component of it will be equivalent to the sine. And now this is also the case for anything that doesn't have a radius of 1. You just have to multiply the horizontal cosine and the vertical sine by that factor. So in this case, our original vector, is VO. So we have to multiply cosine theta by VO and sine theta also by VO. Now this is the same for any value, right? Say you want to break up distance, say you want to break up acceleration. It's going to be the same thing, with the horizontal component being distance cosine theta or acceleration cosine theta, and the vertical component being distance sine theta or acceleration cosine theta. Now you might be asking at this point, why is this important? How does this help us solve any equation? And the reason we break up vectors is because it allows us to solve two-dimensional equations by laying out everything in their x and y components. We have to break up every value into our x and y components, and then we can solve the desired unknown for x and the desired unknown for y. An example problem requiring you to break up vectors could be one similar to this. Say you have a question. Something is thrown up at initial velocity in a certain angle, making a certain degree with the horizontal. Now you are not given what that value is, but you are given the cosine theta of that value, or that value in the x direction. Say you are also given that the distance the thing travels, it goes up and down in the air, and the distance the thing travels is 5 meters. It is asking you to solve how high it travels in the y direction, and what is the angle and what is the value of the velocity originally, without being broken up into any components. Now you might initially think this is unsolvable, but we can solve it breaking up components and looking at the equation in its x and y elements showing you how to solve an equation by breaking it up into its x and y components. First things first, I want to lay out everything we know in the x and the y direction. First, we know that in the x direction, the VO is given. The VO is going to be given to be 20 meters per second, so the VOX is 20 meters per second. The delta x, the distance that it travels in the x direction, is 5 meters as we are given. And now we must break up the acceleration into its x and y components. Acceleration is always just a force straight down. It's pushing something directly back down to the earth. And we defined in the beginning of the problem with the x references up and the y references, with the y references up and the x references down, that directly down is a negative y value. Since the acceleration is directly down, when we break it up into our components, you'll see that it is entirely in the y direction and there is no value in the x direction. You can break it up into several vectors that go down and that go into the x direction, but all those vectors will eventually just end up canceling out in the x direction, and you'll get that it just goes entirely down. So you have something like this, and this one is the one you're trying to solve for. Even if you break them up into into things that go in the x direction, as you see, these will just cancel out in the x direction, as this one goes the same amount out as this one goes in. So we can say that the acceleration in the x direction is 0. Now we have 3 knowns, and we have so we can solve for an unknown. I'm going to solve for the unknown time, as it lets us find the maximum height in the y direction. This is because an object thrown up has a parabolic motion, which means that it travels in a parabola and it reaches the exact highest point halfway between the lowest endpoint and the other lowest endpoint. This means that in half the time it travels, it reaches the height in the y direction, so we can find the time in the y direction once we find the time in the x direction by dividing it by 2. From here, with these 3 unknowns, we can use one of the kinematic equations. I'm going to use the kinematic equation that has delta x, a, t, and VO, as we already know what those all are. I believe that question is delta x equals VOT plus 1/2 AT squared. We know all the values for A, we know the values for x, we know the values for VO, so now we just plug them all in and solve for A. We have 5 meters equals 20 meters per second times time, so 20t plus 1/2 times 0 times t squared. However, since it's all times 0, that part cancels out, so we have 5 equals 20t. Now we can just use simple algebra to solve it. T equals 5 over 20, or t equals 1/4. Now that we know that t equals 1/4, we know that t in the y direction equals 1/4 divided by 2 due to the parabolic motion of the projectile being thrown up in the angle, as I just mentioned. So we know that t equals 1/4 times 1/2, which is equal to 1/8. Now that we know that t equals 1/8, we can solve for the height, as we have an initial known value for acceleration, a, which is the same value for acceleration on Earth, which is negative 9.8, which I will prove later in the video. We have the initial velocity for y, which is we have the final velocity for y, as at the very top of the parabola it is not moving at all. So that value we can set to 0. And now that we have the time, we have 3 unknowns, and we can solve for delta x. So we have, or delta y. So we have the known value time equals 1/8. We have the known value velocity equals 0. The acceleration equals negative 9.8, and we want to find the height. And then after we find the height, if we want to find what the full value for the VO is, we can find the VOX with these 3, or the VOY with these 3 unknowns, and use the Pythagorean theorem to find the VOX, to find the VO. Actually, I am going to solve for the VOY first, as that is in every kinematic equation, so it needs to be known before we can solve the time, or before we can solve for the distance traveled. So in order to find the VO, I have the acceleration, the time, and the initial velocity. So I'm looking for the equation that doesn't have distance at all, and I believe that's V equals VO plus AT. We have everything known except VO, so we can plug it in. 0 equals VO plus AT, or 0 equals VO equals negative AT. A is negative 9.8 and T is 1/8. So VO equals negative 9.8 or positive 9.8 times 1/8. So VO equals 9.8 over 8, or I'm going to call it 10 over 8. So VOY equals 10 over 8. We can now not only solve for the distance it traveled in the y direction, but also what the actual component or what the actual value for VO was, because we can use Pythagorean theorem. First, I'm going to solve for the distance it travels. Now that we have these unknowns, I'm going to use the equation that has VO, delta x, and acceleration. So I believe that equation is 2a delta x plus VO squared equals v squared. So we have 2 times 9.8, or I'm going to call it 10 in this case. So 10 times 2 is 20, times the delta x is the value we want to find, or delta y in this case, plus the VO squared we already found to be 10 over 8. 10 over 8 squared is 100 over 64 equals 0 squared, which is 0. So we can actually subtract the VO and we get 20 times delta x equals negative 100 over 24. But it's important to remember that the a was actually negative, so we get negative 20 times delta x. We can cancel out those negatives and just get 20 delta x equals 100 over 64. Divide both sides by 20, and we get delta x equals 100 over 64 times 20, which equals, give me 1 second, my calculator is not on me right now, give me 1 sec. So that actually totals out to be about 0.01, but I'm going to leave it as 100 over 1,280, over 1,280, and that is its velocity in the y direction. And with that, we can find the regular velocity initial by saying that velocity initial squared equals Vox squared plus Voy squared. As you can see, when you break down a vector into a right triangle and you have these two values, you can still use the Pythagorean theorem, as it is still a right triangle, to find this unknown value. So now we have VO squared equals what we found for the first one, or what was given for the first one is 20 squared, which is 400. So VO squared equals 400 plus 100 squared over 100 over 1,280 squared. I will use a calculator now and find the real answer for that, or I shouldn't say real, but an answer in decimal form, not in fraction form, because that is easier for some people to conceptualize. And yeah. So the actual VO is going to be something close to the VOY, or VOX. So this example wasn't super great because it's going to have a pretty low angle. However, it still conveys the point of the importance of breaking down a vector. We can continue to solve for the delta y now that we have these. We actually have 4 values we can use, but since we have the VO value, the one is essential, that is essential to all kinematic equations, we can continue to solve for that theoretically if we wanted to do that. Now, the next thing that's important to understand about how to solve these how to solve these 3 questions on this FRQ1, I already mentioned breaking down vectors. I already mentioned looking at vectors in both the x and y directions, or looking at components in both the x and y directions when you have 2-dimensional values. I will now talk about what happens to velocity when there is a positive or negative acceleration, as this is important with the problem. When you have an acceleration in one direction and no acceleration in another, what is that going to do to the velocity? What is that going to do to the velocity in the direction of the acceleration? What is it going to do to the velocity in the direction against the acceleration, if there is one? And what is it going to do in the direction? What is it going to do to the velocity in the direction where there is no acceleration? So acceleration is the derivative of velocity, which means that it is the rate of change of the velocity. And if the derivative is negative, that means that the velocity must decrease even if it starts out positive. Because if something has a negative slope, say the acceleration is negative, even if something starts out positive, if it has a negative slope, that means it's decreasing. And since the acceleration is the slope, if the acceleration is negative, then that slope value has to be decreasing, which means that the v is going to continue to decrease, and then it is going to reach negative, and it is going to still continue to decrease infinitely. This is a quick drawing. If this is the graph for acceleration, this is the graph for velocity. The acceleration is always negative, which means the velocity is going to have a negative slope all the way down, continued past here. So now we know that if there's a positive acceleration, but a positive velocity, but a negative acceleration, the velocity is eventually going to turn and become negative, and then it's going to vastly decrease negative infinitely. It's going to get infinitely bigger, decreasing at this equal rate. This is the same if you have a positive acceleration and a negative velocity. It's going to switch, and then it's going to go up all the way and super positive. This is also the case with position and velocity. Say you have a starting position that is relatively high on the y-axis, whatever you define that as. Often people define it as distance to the right, and others define it as distance to the left. If it is going backwards, if it has a speed that is taking it backwards as time goes on, say it's going -5 meters per second, it is going to go backwards at that rate, and it is going to keep going backwards. It's not going to stop until it crosses that 0 point, whatever you define it as, and then it's going to keep going down from there. You can't really represent this with acceleration, since generally when things fall, acceleration is always constant, but the velocity can change. It can actually, like in most, not in most circumstances, but velocity can switch from being positive to negative or being negative to positive. And if that is the case, then the distance will change accordingly. Here I have graphed a situation where you can see the velocity, and you can turn that into the distance graph, as the velocity is the derivative of the distance. This is the slope. What this is saying here is that as a negative slope, the slope is then getting more and more positive, so it gets to 0, and then it's becoming positive. It's the highest right here, most positive, and then it starts decreasing its velocity, becoming less positive, the slope is, until the slope hits 0 again, when the velocity is not changing, and then it's going to be negative. Here I have graphed the distance. As you can see, it starts out going down. It is moving to the left in this scenario as the velocity is negative. However, it is slowing down, which means it's moving less and less to the left as time goes on until that velocity is 0, which means that for that instant it isn't moving. And then the velocity gets more and more positive. It's the most positive right here at this highest point, so it's going to be super positive right here. And then as the velocity starts decreasing, the distance is going to start increasing in slower and slower increments until it's not moving, where that velocity is 0, and then it's going to be negative from then on there, as the velocity is negative from then on. Now we will look at a scenario where there is an acceleration, where there is a velocity, but there is an acceleration that is not in that same direction and cannot be broken up into that same direction, so that no part or component of that acceleration is in that direction. In that scenario, the velocity in that direction would not change at all. It would remain constant, as the velocity has no effect on anything in that direction. Now I want to give you a quick demonstration of the velocity components of an object as it falls or as it is being thrown up over time, as that is quintessential for solving the problem. So we have a ball here that follows this similar path of a parabola until it gets to its very highest point and stops coming down, exactly similar to how it would travel when it was thrown up in real life. It is going to be thrown up at a certain angle, and that angle can be broken down into its two components, its VOx and its VOy. As I was saying, the acceleration is entirely downward. It is the force of g downward, which means it is going to change the velocity in the y direction. However, it is never going to change the velocity in the x direction. So I will show you this drawing in a minute. The velocity in the x direction is going to stay constant throughout the whole thing. However, as it is making its way up to the top, the velocity in the y direction is decreasing and decreasing until at the very top, the velocity in the y direction is completely 0. It is not going to move up anymore. It is completely still in that direction. It is not moving. It has no net movement. However, it still has to the side movement, as that movement will never change. Then from when it's going back down, the velocity in the y direction is being negative, and it's going to speed up more and more negative the longer it falls, due to the acceleration, as I explained, until you get to the final situation, and it should look something like this. You have the thing being thrown up right here. It has. Sorry, I got interrupted there for a minute by my phone telling me I was out of storage space. So as you can see, I've broken up the velocity as it falls or follows a parabolic motion similar of that of something being thrown up in the air. As you can see, I've broken it up into its x and y components, and the y component is going to shrink as it goes up and then start increasing as it goes down, and then the x variable is going to stay the exact same throughout the time it falls. Now in the equation we're looking at, or in the FRQ we're looking at, it's not being thrown up, it's just being followed. It's just falling down. So it would follow this trajectory of the VO in the x direction staying still the whole time, and the VO in the y direction increasing as it falls, starting from rest. We are close to having what we need for solving this problem, although I do think it's important that we talk about what forces are and what a free body diagram is, and then we'll need to find the value of G, just so I am not assuming anything going into this. I can prove it. So Isaac Newton said in one of his first laws that force equals a mass times an acceleration, which means in order to have a force acting on an object, that object needs to have mass and it needs to be accelerating. Okay, so Newton says F equals ma. Now, this means that if there is an object traveling and it has a mass and it is not accelerating, there is no force acting on it. So say something is rolling at a constant speed or traveling at a constant speed, there is no force on it. And since an object in motion will tend to stay in motion, if there's an entirely frictionless surface, a ball rolling will have no force on it, and it will continue to roll forever. So when we look at the first equation, when we look at the example, when we're seeing something have an initial velocity, a velocity is not a force, as there is no acceleration. We are assuming that it is in motion, and it is going to remain in motion, in the same motion, at the same velocity for the entirety of the problem, meaning there is no force in the direction where the second ball is given an initial velocity. However, this is not the case for both balls in the vertical direction. In the vertical direction, they are being pushed down by G, the force due to gravity, and they have a mass, and therefore they have a force, as they have an acceleration and they have a mass. As you can see in the example, and as you know, as I just showed from the velocity changing with acceleration, and how you know when you fall you speed up, you can see that as you fall your velocity increases. Since your velocity is not constant, you must be accelerating, and since you are accelerating, there is a force done on you, and that force is equal to your mass times gravity, or mg, which mg is a type of ma, and I can now prove the value of G using this equation from the centripetal force equation. Gmm over r squared is a force. Since gmm over r squared is a force, we can label it as equal to ma. Usually we use gmm over r squared, which is the constant, which is the value used for calculating the gravitational pull between two objects. Usually we use that in terms of centripetal force, which means we can set that equal to mv squared over r, which is the value for centripetal force, the force needed to keep something at a certain velocity traveling in a circle around it as opposed to just shooting off. However, we do not need to use that in this example, and since it is a force, we can set it equal to ma, and we don't have to set it to equal to mv squared over r. Since we set it to ma, let me talk about gmm over r squared right now. First, basically what it's saying is G is the gravitational constant across the whole universe. It is equal to 6.67 times 10 to the negative 11th, a very small number. The m is a big M. It stands for the mass of the bigger object. And then there's a little m, which stands for the mass of the smaller object. It doesn't necessarily have to be a bigger and a smaller object, say they're the same size. It's just that you define one as one object and the other as the other over r squared. In this case, the big M is the Earth and the small m is the ball. And the r squared stands for the radius between the two objects squared, and the radius is going to be the center of the mass, the distance of the center of the mass squared. So in this case, you might be like, oh, well, you want to find G and you're given these balls. we're not told the weight of these balls, so how can we calculate this? However, we set this equal to ma, and m, this in this case, is the mass of the ball. The force being done on the ball is equal to the mass of the ball times the acceleration of the ball. So we know that this m is for the ball, and we can cancel out this m with the smaller m, and we're left that acceleration equals gm over r squared. Now if we plug in all the numbers, we plug in the mass of the Earth, and we plug in the radius of the Earth, we can say the ball is lying flat on the ground. We're going to get the answer A equal to 9.8, which is what we call g, which is the gravitational constant on Earth. It is important to know that this changes per planet, and you can calculate it out doing this same method. But yeah, this acceleration on any object falling directly from Earth, they're going to experience this same force of acceleration of 9.8 meters per second squared. And they are going to experience it only in the y direction. That is important to know, as gravity is just pointing directly back down to Earth. We are almost able to jump right into the solving of the problems. I just need to go over what free body diagrams are, as they do come up in the FRQ. Free body diagrams are really just looking at the forces on a small scale of a single object. It means when you're given an object, or when you're given a scenario, you want to isolate a single object and look at the forces on it. You mention those forces by vectors. You can break those components up into vectors if you want, but usually they're not supposed to be, although it does help with confusion, and it can show you which vectors cancel out and which ones are equal. It is important to note that vectors of a certain length represents the force and the strength of the force. So a super long force, the vector represents a super big force, and a small vector represents a small force. It is important to know that vectors in opposite directions cancel each other out, as those are forces in completely opposite directions, so those will cancel each other out. I'm going to show you an interesting example of a free body diagram that is going to involve breaking up components of vectors. Say we're looking at a mass on a ramp. You first must isolate the ramp and look at all the forces on it. The first force on it, say it is being pushed by an outside force, and say it is a rough surface. The first force on the ramp is the force downward of the person pushing it downward. As you can see, I have drawn the scenario. I have drawn a vector downward. However, that is not the final free body diagram. That is just simplifying it. The second force is the weight due to gravity, and that is completely downward, disregarding the angle of the ramp, as gravity is always pushing something directly to the Earth. The second force is the normal force, and the normal force is the force of the thing pushing back, as every option has every force has an equal opposite force. Every reaction has an equal opposite reaction, stated by Newton's law. So this means that the normal force is going to push back, the ramp is going to push back, or else the object would just fall right through the ramp. Like say I have this block and I'm putting it on the table right here. It would fall through the table if it weren't for the normal force of the table pushing it up. That is an equal force, and it is exactly equal to the gravity pushing it down. Eventually, if I push something heavy enough down, the normal force of the table would not be able to withstand the force due to gravity, and it would actually give in, and which is why you would see the thing fall. But right now, as it's not moving, the normal force of this table would be equal to the normal force of gravity. Anyway, the ramp is going to push back, but it's only going to push back in a direction parallel to it, or perpendicular to it. Right, it's going to push back exactly opposite it, which means it would go this way, completely up. And then the final force is going to be the friction. I'm making it a rough surface just to make it interesting, and the friction is always opposite of the force added. So now let's break it up and turn it into a free body diagram. We have the object on the thing. We want to indicate the force of the human. We're going to keep first we're going to define our reference points. You see, this is a scenario where you want to define the axes, the reference axes, and you want to define, for simplicity, the y direction to be perpendicular to the slope and to be perpendicular to the ramp, and the x direction to be parallel to the ramp, for simplicity. I'll show you why, because it means we can break stuff down into, we can break components down into what are perpendicular and parallel. So I'll show you one free body diagram where I don't break anything down, and then I'll show you a second one where I do. So this is going to be plus x and this is going to be plus y. When we don't break anything down, we have this and we have this. And it looks a little something like this. Now when we do break things down, we can break down the mg into a force perpendicular to the ramp and a force parallel to the ramp. The force perpendicular to the ramp is going to actually be the mg cosine theta. We're breaking it down along those axes. As I said earlier, you see if you draw it out, combined with these axes like superimposed, you can see that you have this plus y plus x, and you have this mg, and you can break up this mg to follow these x and y axes. I should draw this x continued down, so you see very clearly that you have this vector, and you can break it up into these two. So I am going to break up, and the mg cos theta is actually going to be the point perpendicular, because the theta, which is the same as the theta equivalent to the ramp angle with the horizontal, is going to be this degree in here, if you can see it. And so that means that this is mg cosine theta, and then that going perpendicular to the ramp, pushing it down, you're going parallel to the ramp, pushing it down, you have the mg sine theta. So that is what's doing the pushing. You also have the force applied. That, since that is on one of the reference or one of the defined axes, we can't break that up anymore, and we shouldn't. And the friction, which is also going parallel to a reference axes, and the normal force, which is again parallel to a reference axis. Now you can see that the mg cos theta and the normal force pushing it are canceled out, and you have the two net forces, or the three net forces acting on it, or the mg sine theta, the force applied, and the friction going the opposite direction. And that is basically all the free body diagram knowledge we need to have going into solving these FRQs, and this is basically all the catch-up knowledge we need to have going into solving this 2015 AP Physics 1 free response question. Now let's revisit the first question. I am probably going to reread it to you, as it's been a while now since I've read it, and I want to keep it fresh in your head. I will show you the diagram first off. This is the starting diagram. As you can see, two balls are released from the same height, although one is given initial velocity, so it follows this path, and they are both dropped. Let me reread you the scenario. Two identical spheres are released from a device at time t equals 0 from the same height h as shown above. Sphere A has no initial velocity and falls straight down. Sphere B is given an initial velocity of magnitude VO and travels a horizontal distance d before it reaches the ground. The spheres reach the ground at the same time, TF, even though sphere B has more distance to cover than the other sphere. I'm going to explain this. This is actually one of the questions, although I have given you the information already to solve this. I will also make it clear. But first we'll talk about the first problem. Air resistance is negligible, and now starts part A. The dots below represent A and B, so there are two dots, and it is asking you to draw a free body diagram labeling all the forces. I'm going to do it on this scratch paper, and then I will show you my final answer, which is what I put on the FRQ. So we have these two dots. We all know that force equals ma, as I covered in previous minutes. So the force being done on the object, in order for the force to be done on the object has to have a mass, and it has to be accelerating. And in the first sphere, with sphere A, this answer is quite obvious. Sphere B, it's a bit less intuitive, but for sphere A, it has mass, and then what direction is it accelerating? Well, it is not accelerating in the x direction. First things first, let me define my components. Up is y and down is x, just straight up, straight down, as I put right here. And it is very clear it is not accelerating in any direction other than the direction gravity is pulling it down, which is clearly just the direction straight down to Earth. So I can draw a free body diagram. As it is falling, it is asking for a free body diagram at t equals 1/2 of its final. Its final t is when it touches the ground, so t equals 1/2. So in this scenario, it is still in free fall. It is not on the ground. It has no normal force to cancel out that gravity, and air resistance forces are negligible. So the only thing pushing it down, the only force acting on it, is its mass times the acceleration due to gravity, which is mg. So I'm going to leave this as mass times gravity, but you can also leave it as mass times 9.8. And there we have our first vector, mass times 9.8. Let me label that sphere A. Sphere A. Sphere B is a little less intuitive because it is given an initial velocity. However, as I explained earlier, velocity is not a force. Initial velocity has no force. We are assuming it already has that velocity, so it isn't accelerating to get that velocity, and in the x direction it is going to stay at the velocity the whole time, since it has no acceleration in that direction to cancel out the velocity. As I talked about earlier, acceleration only changes velocity in the same direction. So since it has no acceleration in the horizontal direction, it has mass, but it has no force in that direction, which means no matter how much of an initial velocity it has, no force is going to be acting on it to move it in that direction, unless we are assuming that it is being pushed in that direction. But here it just says it has an initial velocity. We're going to assume it has already had that, and therefore it has no force acting on it now, even though it might have needed one earlier to get it going to that speed. As long as it is not accelerating, it has no force acting on it. Therefore, it is clear when you look at it and you break it up into its dimensions, you see it has none in the x direction, and it does have one in the y direction, as there is that force due to gravity that's acting on it, that is also acting on the other one, as it acts on all things. And it is also in the air as the other one is, at the exact same distance, because they do fall at the same rate, as I will explain, and therefore we can write the free body diagram for it, and it is also just an arrow straight down labeled mg. I think we're supposed to assume the spheres have the same mass, but if not, then it's mbg or m2g, or m times 9.8. And your final answer should look like this, or as I wrote on my FRQ packet, this, just two equal arrows of equal magnitude being pushed in the same direction. Thank you. Question B, like all the other questions I have given already enough background information to solve. Right now it is just putting it together and reconsolidating what we have learned and applying it to the physics FRQ and the physics 1 AP test. So question B is, it's giving a graph and it states, on the axis below, label a graph of the horizontal component of the velocity of sphere A and sphere B as a function of time. Now this is important. This comes up with breaking up components, breaking up vectors, as we are looking at the vector in the x direction. And so let's start with sphere A. As I mentioned, both spheres follow, well, actually sphere A doesn't follow, but sphere B, I'll get to that later, but it should still follow that parabolic motion of something that is falling or something that is being thrown up and falling, except you are not looking at the part where it is going up. But I will start with sphere A. Sphere A, you want you to graph the horizontal component of its velocity. Now, as we are seeing, as it is given, it starts at rest, and it is given no initial horizontal velocity. And as I have shown you, when something falls straight down, it has only one accelerating force acting on it, and that is the force due to gravity. It has no accelerating force going from a different direction. So we can assume the only force acting on it is gravity, since it has mass and the gravity has an acceleration, and there is nothing giving it an acceleration in another direction. Now, acceleration, as I already said, affects velocity, and accelerating something from rest will give it velocity, as acceleration is change in velocity. So this 9.8 meters per second squared of gravity is meaning that the acceleration is changing at a constant rate of 9.8 meters per second, which means it starts from rest. The first second it's going to be at 9.8, second, as you can see, etc. So we can see that as we break it down, the velocity is going to be decreasing as it falls, or increasing negative infinitely, right? Obviously it's going to hit the ground at one point and stop, as the ground is actually doing a force upward back on it, causing it to decelerate, and therefore doing an equal force back up on it, causing it to stop. However, if there was no ground, it would just gain velocity infinitely. However, Since there is no force in any other direction, as I explained, it is actually not going to have any velocity component in the x direction. So therefore, the component of it as time goes on is going to be completely flat and it's going to remain 0. Now let's talk about the velocity in the horizontal component of the second sphere. Now, as I showed you with the parabolic motion and with something falling, and as you know, force equals ma, there is still no force in the horizontal direction. You can see that from the free body diagram, and you can see that, as I said, from F equals ma. There is no force in the horizontal direction, which means there must be no acceleration in the horizontal direction since it has a mass, and since force equals 0, you have 0 equals ma, a equals 0 over m. Doesn't matter what m is, a would have to equal 0. So, with that being said, we know it is not accelerating in the horizontal direction. Since there is no acceleration affecting it in the same direction, that initial velocity is going to remain going forever. Now, the reason you don't see this in life when you push something is because of frictional forces and because of air resistance. But in this situation, when we are neglecting all of that, it's going to fall and it should continue traveling with that same exact velocity forever. Therefore, when you graph it as a matter of time, that initial velocity will not change. It is not going to be 0 though, as it does have an initial velocity we'll mark as VO, and it is too going to be a straight line, except it is not going to be a straight line exactly on the y-axis or on the x-axis. It is going to have a certain x value, but that value is going to be constant. So let's label this sphere B and this sphere A, and this should be what the answer is for the FRQ. It should look a little something like this. This is the graph. Let me label my axes. You have time, and you have VOX. I'm just calling it, or VX, not VOX, VX. And there you have it, part B of this first FRQ. The third and final question in this 3-part FRQ in this 2015 AP Physics 1 free response question is to write in a clear, coherent paragraph length response, explain why the spheres reach the ground at the same time, even though they travel different distances. Include references to your answers in part A and part B. Now this I have also addressed, and it has involved, as I talked about earlier, breaking up a situation into its x and y components. So we know for sphere A, there is only one component. There is only the y component. It has no velocity in the x direction, no acceleration in the x direction, and no distance traveled in the x direction. So let's say delta x equals, it could equal anything, we'll call it delta x. VO equals 0. V equals V, it doesn't matter what it is. Acceleration equals A, and it wants you to find the time. We can use a kinematic equation with the unknowns, although it's not necessarily necessary. You can think of it conceptually, but time equals time. Let's use, which equation should we use? Let's use V equals VO plus AT, and we get V equals 0 plus AT. Oh, A equals 9.8, by the way. V equals AT. And the time equals the velocity over the acceleration, or V over... I should mention this V is VOY, although it's not very important because that is assumed. Since it has no velocity in the x direction, we do not need to break that down. So, so V equals... Okay, I think I might want to use a different kinematic. Okay, never mind what I was saying a minute ago, because actually we'd have to use the quadratic formula otherwise, which would get sort of confusing. So let's isolate t, and t equals velocity over acceleration. So now we should look at sphere B. So we have these unknowns, however, they're known in the sense that 1 equals V and 1 equals A. And now let's look at sphere B. Now this one involves breaking components up into the x and y directions. And since there's no acceleration in the x direction, we know that velocity doesn't change. And I'm going to start by breaking it up into the y direction, as that is the one that's important when it is falling, and that's the one that's going to tell us the time. Since a is only y, let's look at v in the y and find out its time. It has no acceleration in the x, so the x would be kind of bland. The x is just going to be that vox, and then it's going to have that final velocity of the equal to the vox2, because the velocity is not going to change. It's going to have no acceleration, and it's going to have a certain distance traveled. However, that isn't going to be important. So let's look in y. In y, the distance traveled is delta y. The VO is 0 as it starts from rest in the y direction. The V final is going to equal V, and it is going to be the same V as in the other one, because when you look at you dropping something versus something else falling, if you break it down into the x component, it is still accelerating at the same rate in the x direction, which means the velocity in the x direction is still going to change the same amount, right? It's accelerating down at negative 9.8 meters per second. That still means that after the first second, it's going to be negative 9.8 meters down, then it's going to be negative 9.8 times 2. So it is going to be the same thing in the y direction as you go, and the x direction is going to be unaffected due to the acceleration not being in that x direction. So the acceleration equals 9.8 and the time equals t. And we can solve it the same thing using v equals at. Get a t on its own, gets a on its own, and you get t on its own, and you still see that t equals the v over the a, and the v is going to be the same, and the a is going to be the same, and therefore the time is the same thing. That's how you can prove it mathematically, but you can also explain it just conceptually, saying, hey, look, there is no acceleration in that x direction. All the acceleration it's experiencing is in the y direction, same as the first ball, and it is dropped with the same initial velocity in the y direction. And when we're looking at the time it takes for the thing to fall, we were only looking in the y direction. So they have the same values for the y direction, and since that is the case, this x direction for the other one, it's not going to affect the y direction at all, and therefore it is not going to matter, and it is not going to take a different time to fall, despite using the same thing, because the falling is all a y direction fall. It is no x direction in this fall. It is the time it takes from here, and therefore it has the same properties. It is going to fall at the same rate, even if this is going down at a certain velocity. This velocity is unaffecting the way it falls in any other direction, so therefore it is going to fall at the same time. If you think about it, you can't break up that initial velocity into something that affects the y direction. And since an initial velocity in the y direction would cause it to fall faster or slower, as I already said, it wouldn't change. Like, say you could break it up into velocity that was going upward, it would take a little bit longer to fall because you still have that velocity going up at first that needs to slowly adjust as the acceleration is down. And say it already is going a bit down while the acceleration is down, it is going to increase downward, but it's already going to have that starting boost. But since you can't break up that VO into any other direction, that VO that is given in the x direction, it is going to fall at the same time in the y direction. In the paragraph on the actual FRQ, I stated each sphere lands at the same time because they both have the same initial velocity in the y direction. It is both 0. They are both starting from rest, and they both experience the same acceleration downward or in the y direction. Although sphere B has an initial velocity, all of its velocity is in the x direction, and it is still starting at the same downward speed, that speed being 0. Since the ball has no acceleration in the x direction, it does not lose any velocity in that direction, and that is my final answer for the third part of this FRQ.